Okay, okay. Let's study a bit once again. My computer might be too noisy. Let's see if I have proper commands near. Yes, I do. Tac, tac. That way, it will probably not make too much noise. Anyway, so let's review what we learned yesterday, learn the rest of it, and learn a bit again of this one. I'll have to get my stuff from the washing machine downstairs in a minute, in 20 minutes. Anyway, so this is a general pseudocode for genetic algorithm. Of course. What a question. Let me even put that here. Let me check how loud it is. Okay, it's properly loud. So a tournament chooses one parent, children, offspring, new individual from the combination of two parents with yes, combination and mutation. Then you stop, initialization, number of function evaluations, solution interpreted in that's the phenotype, modification it's the mutation, that's the selection, phenotype it's the solution interpreted in the solution space from the genotype of the individual. You start by initializing the population. Individual it's one solution to the problem, a candidate solution. Yes, okay, candidate or not. Initialization, evaluation, selection, representation of individual manipulated, that's the genotype, and then you just return the best individual of the last population. Okay, so the loop is selection, combination, mutation, and then you have like replacement, or maybe you have rather evaluation and replacement. Selection, combination, mutation, evaluation, replacement. Great. Parent, it's the individual chosen for reproduction. Fitness, that's the quality per se of an individual. I have this little inconsistency where the recto it's slash and in the verso it's 2 points. I'll have to modify that when I have the energy for it. Anyway, main steps for genetic algorithm. So you have initialization, selection, combination. Oh wait, we have before that we have evaluation, selection, combination, mutation, replacement, and stopping. I don't think replacement was cited as a step. Stop. Ah yes, it was. Well, great. I've put it. Init eval select. Yes, okay. So evaluation, selection, NFE. Yes, that's the replacement. Ooh, the whole algorithm. So you initialize first relation, evaluate this relation while you have your NFE is below the threshold, a budget, you have selection, combination, mutation, evaluation, replacement, and then you return best individual. And that's it. You have initialization, evaluation, while, selection, combination, mutation, evaluation, replacement, return. Perfect. So as we said, selection, mutation. Initialization, you just initialize a new population with random individuals. You take 2 individuals. I have not described the crossover process, where like the base crossover, you just take a point and blah blah blah. That's too bad. So anyway, crossover here, well, you just combine 2 parents to produce 2 children. Generally 2, but it can be 1 or more. By default, mutation applies only to children. Evaluation, replacement, selection, combination, that's the parent. Combination, mutation, evaluation, you do another tournament to have the next parent. Population, it's a set of individuals at a given iteration, yes, whatever. Pseudocode, general pseudocode of the genetical algorithm, well, we had it right there. Trust me, it's in my brain. While NFE is less than a certain budget. Selection, you select the parents via a tournament for crossover. Initialization, evaluation, selection. Combination, sorry, was a bit far. Set of individuals, that's population. Initialization, replacement. Via elitism, you keep some parents and some children, and it depends on your policy. New individual produced by crossover mutation, that's a children and offspring. Haven't we already had this question? Yes, we did. Mutation. You apply some changing in the genotype of the individual based on some probabilities. The algorithm stops when no more NFE. Evaluation. Sorry, I'm a bit not focused. Well, we're still really fast, but that's a very simple deck. Anyway, evaluation. You just compute the fitness of all individuals. By default, what does elitism? It keeps 1 or several best parents and fill the rest with best children. Replacement. That's the main steps of the genetic algorithm. And they are, but we already had this question again, but simply it was not like we didn't have the hints of number of bullet points. The genotype is the representation of the individual manipulated by the algorithm. Combination, well, that's just the crossover step. Solution is an individual. Simple, very simple. But see, we had some information lacking a bit. maybe do this one here, I think. Oh, we have more cards than yesterday somehow. Oh no, what did I do? Given X an image and F neural network, a weighted network rather. Instead of modifying weights, we modify pixels in the image. We can feed. Why do I have this question again? Because I was correct yesterday and it's a generally correct question, so that's a bit weird that it still pops today. Anyway. So if mod collapse happens, we feed real images in a batch and generated images in another batch, so that way we can count how close to one another images are. See, we had this question yesterday again, and it was when I clicked on. That's weird. Anyway, so that's one step non-targeted attack. First step, you retrieve the gradient of the prediction loss compared to the image. You keep only the sign of this gradient, and then you replace x with x plus epsilon times sign of the gradient of x of the loss x1 x plus epsilon sine delta x. Correcto. That's deep convolutional GAN. To stabilize training, so you normalize data, that's true. You use bounded activation function for generator, I think. Yes. Structure of a DC GAN. BEAM was proposed by Kurakin in 2017. Generator learns a nonlinear transformation from noise to image space, which does this. The two players are in a mutual optimum. They are stuck in mutual optimum. For deep relative learning, you send to the oracle the images with the smallest default value. Properties of adversarial examples. I'm sure we already had that. Different from outliers. Resist to regularization. Produce high confidence in prediction. And the last one is simply transferability. Yes, simple. In what domain? In active learning with marge. Generator learns, transform, blah 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 blah. The parameters are optimized for to make images realistic. Okay, perfect. Let me check some. Anyway. So what is homoscedasticity? It's simply you have your two data groups. Is the variant of both more or less similar? analysis where we compare several algorithms. Okay, but well, it's just like a single problem analysis. Okay, so non-matched, parameterized, and for two groups t-test. That's the alpha. And see how this card is not properly formatted. We forgot this here. That's the alpha. Hypothesis by default, it's the H0, it's the null hypothesis. That's okay, so let's try to write it. It's homocédasticité, I think. Homocédasticité, yes. CRN. What's used for? It's used to add the matched property to reduce variance. H1, it's the supported hypothesis, which generally states that there exists significant, statistically significant differences between both data groups. So to choose a test, first you check if your data are because here we have three tests here: independence, homodesta, and normality. Then you check if you have like two or more algorithms to compare. Yes, number of groups, not algorithms, groups. That's proper. Quantity that measures. That's the p-value, as far as I'm concerned. Choice of test. Man-Whitney, well, it's still like when you have two groups. Common random number. So you check number of groups, you check if they are, and then you check the parameterized test assumptions. That's the alternative hypothesis H1. Two groups. Normality is do the data follow more or less normal probability distribution. Okay, interesting. Paired t-test, it's when you have matched data and parameterized data. Data such that each observation corresponds to a group. Oh, that's the matched data. So when it's like non-parameterized, okay, and non-matched. Non-parameterized means it's not a t-test. Non-matched, I think it's the Man-Whitney U. Because if it was matched, it would have been the Wilcoxon. See? I learned fast. Two groups. Pipeline to do what? Pipeline to choose a statistical test, the proper statistical test. So yes, if you have non-parameterized but paired data. Non-parameterized but paired. Non-parameterized data, simply data where samples have no correlations from a group to another. Like, I don't know how to explain it. Seeds are not set the same between those groups, if you wish. So, to choose a test, you first check number of groups you have. God damn. Then you check because I know you check like parameterized assumptions. So which one is this? You have the number of groups matched, you just check for matching, I think it is, and then you take your test. Yes, exactly. Okay, I have to grab some clothes from the washing machine. Give me a moment, please. Okay, so anyway, I'm back. I did a bunch of stuff, and we can resume studying. And I'll have to leave anyway in like 20 minutes again. Let's see how much we achieved in 20 minutes. So productive. Anyway, so what are matched datas? Datas are matched when datas from both groups share a characteristic, for example, the seed or anyway. So if you have matched data and parameterized, then you need matched t-tests, paired t-tests. Yes, paired matched. You get the idea. Non-parameterized test. We use them when datas don't respect the parameterized assumptions. You choose a test. Alpha is the value you set under which you consider the outputs of the tests are non-significant. And do you reject or not H0 based on that? Two groups, non-paired but parameterized t-test. Data's normality runs its independence when it's non-parameterized and non-paired. These are tests you perform after the main statistical tests, generally when you have more than two groups, to determine between which pairs you have statistical differences. When do we reject HO compared to alpha and p-value? When the p-value is below alpha, you reject H0. What does it mean when p-value is small compared to H0? If the p-value is small, it just means that H0 that the data does not support H0, so you need to reject it. Single problem analysis, simply you analyze an algorithm, for example, on only one. I mean, you can analyze one or more algorithms, but they all are run on one benchmark only, and not several problems or bench. Sorry, I'm just planning the next move. Anyway, so this is correct. These are post hoc tests. H0 null hypothesis. It's the default hypothesis, which generally supports that there exists no significant statistical differences between algorithms or data more generally. What tools allow to do that? The common random number CRN. Okay, so t-test you need paired data. I'm thinking that I should have created cards where this is also hidden at the same time as this one. So you know, because tests also depends on how many groups you have. Anyway, so yeah, t-test parameterized and non-paired. Independence, when you repeat the runs for statistical significance, and one run is not influenced by the previous one. So you, oh well, it's right here. You check, but I didn't watch. You check number of groups. You check paired or not. You check for parameterized. You check what test. I went fast, but maybe it was wrong. Number of groups, paired, parameterized, hypothesis. No, that's correct. A very low p-value. Does it prove H1? Okay, so very low p-value for H0. No, it does not prove it. It only rejects H0, yes, exactly. Simple, very simple. Data is such that there exists explicit correspondence. That's paired data. Whoa. There is not, so it's non-paired data. That's correct, but anyway. Pipeline of statistical to choose. So we said to determine, I'm not watching on the right, determine group number, determine if data are matched or not. Type of statistical test that suppose, okay, so these are parameterized tests. And as just seen, these tests suppose normality, independence, and homoscedasticity. Like CRN p-value is simply the value returned by the tests that supports or not the hypothesis. And yes, it translates to how much the tested data are compatible. Anyway, so when you have paired data but it's non-parameterized, that's Wilcoxon test. Okay, so now the rest of this deck. It's going to be like yesterday, simple this day, but tomorrow it will be more difficult. These tests stuff. This coffee is very good. So if you have, let me restart the counter here. If you have more than two groups and you are non-matched but parameterized, you do ANOVA. Okay. So ANOVA, you're parameterized but non-paired. Okay. One way ANOVA. So I guess there is like both way ANOVA or something. Ah, see? It's like the t-test kind of. So that's easier to remember because there is like logic between some tests. So more than two groups, and without even looking at it, I can guess that it is like parameterized and paired. And this is, sorry, repeated measure ANOVA. Okay. Now, when it's more than two groups, non-matched and non-parameterized, Kruskal-Wallis. Okay, so nothing. When you have more than two groups and nothing, Kruskal. Okay, Kruskal-Wallis. Okay. And if you have, okay, so it's like Kruskal-Wallis is the equivalent when you have more than two groups to the Whitney U. It was the name of the test, right? Whitney Wilcoxon Manu. And the other one was Kruskal-Wallis. These names are getting mixed up in my head, kind of. I ain't gonna lie. So anyway, so when you have still more than two groups, and you only have paired datas, Friedman. Okay, Friedman test. Alright. So see how this card is a bit ugly. What do you mean, Mo? To have things neat and clear. Comparison when more than two algorithms. What to do if the global test rejects? You need to run post hoc tests to see what pairs are different. And here too, I need to clean this a bit. Okay, so this is learned. This is good. And I have to be on the go in very little time. Very little time. Thinking about what I should wear to the event. So this is a good thing that we've learned both this weekend. Well, it was not that much work, but it's always good to have it down the line. And now I'm just thinking about what to do. I think I'll stop it here and maybe resume after the event in the evening. Do a bit of work still. I don't know what work we'll do, but we'll see.